Hi, hello, welcome back. Okay, so this is our second video for operational amplifier, and for these videos, we're going to discuss the two basic op-amp circuit, which are the inverting amplifier and the non-inverting amplifier. Okay, so to start with, we will be discussing the inverting amplifier. Okay, so the inverting amplifier is, we can say, the most basic op-amp circuit. Okay, so um, we have here this type of amplifier. As you can see, this uses a negative feedback to stabilize the overall voltage gain. So where is the negative feedback here? So the negative feedback is our RF here. Okay, so why do we call this a negative feedback? Because from the output, it goes back to our input, and particularly the inverting input. Okay, so we call this as your negative feedback. Okay, so why is there a need for a negative feedback? Okay, so as we discussed from the previous video, the open loop voltage gain for an operational amplifier is too high, okay? And since it is too high, it is unstable to be used to be of any use without the form of feedback. Okay, so usually it is between the range of 20,000 to 200,000. Okay, so this is a very unpredictable voltage gain, and this voltage gain will be useless. Okay, so therefore we place a feedback to somewhat stabilize our overall voltage gain. Okay, so as you can see, we kept the figure simple by eliminating first, or by not showing first, the power supply. But always remember that we always have a positive and a negative voltage supply in our operational amplifier. Okay, so to start with, we have an input VI. So this is our VI. This is your V in, which is directly connected to the inverting terminal of our operational amplifier. That's why we have here an inverting amplifier. So your VI drives the inverting input through our resistor R1. This is our resistor R1. So the inverting input V2, okay, so the inverting input V2, this one, plus or minus V2 here, is amplified by the open loop voltage gain to produce an inverted output voltage. So if we have here our input voltage here, as you can see, you have an amplified voltage with a 180 degrees phase reversal. So we have an inverting amplifier. Okay, so our RF here, so output voltage is fed back to the input through our feedback resistor RF. Okay, so RF results in a negative feedback. So because the output is 180 degrees out of phase of your input. Okay, so how can we say that the feedback resistor somewhat stabilizes our overall voltage gain? Okay, so if our open loop voltage gain increases for any reason, so it increases significantly, so the output will increase. Okay, so once the output is increased, feedback it will feed back more voltage to the inverting input. Okay, so which reduces V2. Since this is negative, it will be opposing, so it will cause in a decrease in V2. Okay, so let's repeat. Once our open loop voltage gain significantly increases, so it produce an increased, okay, uh, so an increase in output. Okay, so that output will be feedback to your circuit, which makes your V2 smaller. Because it is negative, it will be opposing, so that means since V2 becomes small, even though our open loop voltage gain increases, your output will not, or will just very slightly increase. Okay, so small that it is hardly noticeable. Okay, so therefore, if we have an increase without the feedback and your open loop voltage gain increases, your output will be increasing significantly. But because of the feedback here, okay, so your V2 here will be adjusting to whatever increase in our open loop voltage gain. Okay, so because when the output increases, the feedback also increases. Since this is negative, okay, so it will cause a decrease in our V2. So if this is quite smaller, even though the voltage gain increases, so your output will not be or will not increase significantly. So that is how it stabilize your overall voltage gain. Okay, so the output voltage is fed back to the input through feedback resistor RF. Any changes in V2 produced by the input voltage are opposed by the output signal. Okay, so that is the effect of our negative feedback. Okay, so we have here what we call the virtual ground. Okay, so when we connect a piece of wire between some point in a circuit and the ground, we all know that the resulting voltage there will be equal to zero. At the same time, that wire from some point in the circuit and the ground will provide a path for current to flow to the ground. So that specific wire, okay, that particular wire, we call that a mechanical ground. But that is very different from the concept of virtual ground. So what is the concept of virtual ground? Virtual ground is widely used shortcut for analyzing an inverting amplifier. So very virtual ground actually is very unusual. Why? So it is just like a half ground. Why? Because it is a short for voltage, yet it is open for current. Okay, so we all know that when we have a short circuit, your voltage is zero, but your current is maximum. Okay, but this virtual ground here is very unusual because it is short for voltage at the same time. Since it is not there, it is just virtually there, it is open for current. So the virtual ground is provided for us to have a very simple approach in our analysis of an operational amplifier. So the virtual ground is based on the ideal op-amp characteristics. So what are those ideal op-amp characteristics? So this is our virtual ground. As you can see, it is in a form of a broken lines. Okay, so what do we mean by the broken lines there? So this is just for our assumption. It is not a mechanical ground in such a way that there is really a real wire that is connected from this point going to the ground. So we are just assuming that there is a virtual ground there, and we are basing that on your ideal operational amplifier. So what do we mean by that? Okay, so since Rin is infinite, so what do we mean by Rin is infinite? We have a very very high input impedance, and if we have a very very high input impedance, that makes our I2, the current entering your operational amplifier, equal to zero. Okay, and another ideal characteristic of our op amp is our open loop voltage gain is infinite or very very high. So if we have a very very high voltage gain, so voltage gain is equivalent to output voltage divided by V in. Okay, so how are you going to make your voltage over open loop voltage gain infinite? So if our V in is equal to zero, so therefore we are going to assume that this is equivalent to zero. This is our basis for our virtual ground here. Okay, so we're going to assume that no current will enter your operational amplifier, and at the same time, our voltage, okay, the input voltage to your operational amplifier will also be equal to zero. Okay, so the voltage gain So the voltage gain for our inverting amplifier is given by this one. So this is what we call AV, so for voltage gain, and this time we have a closed loop. So it is no longer open loop. So our usual value for a 741, which is 100,000, okay, so this is no longer equivalent to 100,000 because there is already a loop, okay, in the form of our RF. Okay, so the closed loop voltage gain, this is the voltage gain when there is a feedback path between the output and the input. So how did we arrive with negative RF all over R1 here? So since we have here a virtual ground, that means no input will enter our operational amplifier. At the same time, no current will enter our operational amplifier. That only means that all of the current coming from our Vin will directly flow across your feedback resistance here. Okay, so if you're going to look at our circuit there, what is our Okay, so what is our input there? Our input there is equivalent to your Vin. So your input voltage there is equal to Vin, and that is equivalent to In multiplied by R1. So this is your input voltage. Okay, now, what is our output? If we're going to look at your output, okay, so your output is directly connected across your RF. But this is the negative sign, okay, the negative terminal for your output. Meaning, the negative terminal for our RF because your current will enter here, this is positive, and your current will leave here, which is negative, giving us our V out, which is connected at the negative terminal. So that will become our V out is equivalent to negative, okay, In multiplied by your RF. Okay, so what is your closed loop? So this time, your CL there stands for your closed loop. So what will be your closed loop voltage gain? So your closed loop voltage gain is simply equivalent to your output voltage divided by your input voltage. So what is our output voltage? Our output voltage is minus I input multiplied by RF divided by our input, which is equivalent to I input multiplied by our R1. Since we are talking about the same input current because no current will enter your operational amplifier, so we're just going to cancel this out, leaving us our voltage gain equivalent to minus RF, or the feedback resistance, divided by R1. So this is the closed loop voltage gain for any inverting amplifier. Okay, so the negative sign there signifies that there is a 180 degrees phase shift between the input and the output signals. Okay, so as we can see, we have a very, very simple design here. Okay, so we will have what, for example, you are the designer and you are asked to build, okay, an amplifier wherein your output will be 50 times of your input. Okay, so all you have to do is to get an op amp and then connect a 50 kilo ohms at the feedback resistance, and then a 1 kilo ohm at your R1. So 50 kilo ohms divided by 1, that will automatically give you a negative 50 voltage gain. So the point that you place your input at the inverting terminal, that will already give you an automatic inverting output. So that is how your operational amplifier works as an inverting amplifier. So what is the counterpart of the inverting op amp in our previous discussions? So this is just like a common emitter configuration, because if you have a common emitter configuration, you will have an output that is 180 degrees out of phase with your input. However, if you are going to be asked to design a common emitter amplifier with a gain equivalent to 50, you cannot just give the design right away because you still have to consider your circuit. What will be your R1, what will be your R2, what will be your RC, what will be your RE. So you will be starting with the DC analysis, you will be going to the AC analysis because before you can even solve for your gain, which is equivalent to 50. But this is a very very straightforward approach. Okay, I want to change my gain. I want it to become 100. So what are you going to do? So you just change your RF to 100 kilo ohms, and then our R1 is still equivalent to 1 kilo ohm. So that is already a change in your voltage gain. Okay? So as you can see, there is no characteristic of op amp anymore. So when we are talking about inverting amplifier, what tells you, okay, what parameter gives you your voltage gain? It is not anymore what op amp you are using. So your gain will be dictated by what value of RF and R1 that you are using. Okay, so it says here that the ratio of the feedback resistance to the input resistance will tell you how much is your voltage gain. Okay? And automatically, we have lessen your open loop voltage gain, because if this is 741, the open loop voltage gain of this is somewhat near 100,000. But because we make use of a feedback, we somewhat reduce that into a more usable and a more practical value of a voltage gain. So this is how your inverting amplifier will look like compared to a common emitter configuration when we are going to make use of an op amp. All you need is the value of your feedback resistance and your R1 here. Okay? So, talking about the input impedance for an inverting amplifier, so the input impedance with closed loop circuit is just equivalent to R1. So, for example, our R1 is equivalent to 1 kilo ohm, so that is already your input impedance. Unlike for common emitter configuration, in solving for the input impedance, you still have to solve for the emitter current and then solve for the small RE and then multiply it by beta so that you can get your input impedance. So in an operational amplifier working as an inverting amplifier, all you have to do is to look for the value of of R1, and therefore that is already your input impedance closed loop. Okay, so for the bandwidth, okay, so the greater the negative feedback, the higher the closed loop cutoff frequency. Okay, so the smaller your voltage gain, closed loop voltage gain, the higher your F2. So what is F2? F2 is your cutoff frequency, okay? Or that is where your frequency will start decreasing. Okay, so as you can see, if your voltage gain is very very high, you have a lower cutoff frequency. But as your gain decreases, your F2, likewise, they increase. So technically, it is a trade-off. What do you want in a circuit? Do you want a circuit having a higher gain? So therefore, our frequency will just be limited. Or if you want a somewhat lower gain, then our frequency will not be limited. Remember, the frequency dictates what application are you going to use your op amp. Okay, so we have here your F2 or your cutoff frequency. So every time, all will start with 0 because this is an operational amplifier. This is directly coupled. Okay, so our question is what will be your upper cutoff frequency? So that is equivalent to F unity divided by the closed loop voltage gain plus 1. However, since your closed loop voltage gain is somewhat greater than 1, okay, we can neglect the value of 1. Okay, so that will simplify our formula to F unity, which is equivalent to the closed loop voltage gain. So in solving for your F unity now, that is equivalent to the closed loop voltage gain multiplied by your F2 CL. Okay, or the upper cutoff frequency. So this F unity now is no longer equivalent to 1 megahertz. Okay, so that will be equivalent to 1 megahertz if our gain is equivalent to 1. But if we have a higher gain, it will no longer be equivalent to 1 megahertz. And F unity here is what we call the gain bandwidth product. Okay, so why gain bandwidth product? Because this is a product of your gain, which is your closed loop voltage gain, and your F2CL, which is your bandwidth. Because since we start with 0, any value of F2 here will give you the value of your bandwidth. Okay, so this is called the GBP, or the gain bandwidth product. For the bias and offset, so this is just the same with our differential amplifiers and with the values that we have discussed in our previous in our video number 1. Okay, so bias and offsets, the negative feedback also reduces the output error caused by the input bias current, input offset current, and the input offset voltage. Why? Because the although this one will be constant, okay, so your V1 error, your V2 error, your V3 error, we have already discussed this in our previous video, our gain here will technically go down. Okay, so unlike before, if this is open loop, this is equivalent to 100,000. But if we decrease your closed loop voltage gain, therefore, we are also decreasing our error voltages. Okay, so we have a resistor compensation and offset nulling. So usually, this is equivalent to our RB2 in our formula will be equivalent to R1 parallel RF. Okay, so to nullify or to help uh, offsetting this bias and offset currents and voltages, we usually place an RB1. So instead of grounding it, we usually place an RB1, which is instead of grounding your second input, we place an RB1, which is always equivalent to your RB2. So later we will be discussing that. Okay, so we have here an example. It says here, so what are the closed loop voltage gain and bandwidth? And what is the output voltage at 1 kilohertz? And what is the output voltage at 1 megahertz? Okay, so we have this solution for that. So the voltage gain is very simple. Okay, so how do we solve for the voltage gain? So the voltage gain is equivalent to RF, okay, which is your feedback resistance, which is equivalent to negative 70, minus. So the minus is because it is an inverting amplifier. So that is 75 kilo ohms divided by 1.5. We have a gain which is equivalent to 50. So the output will be increased 50 times, and the negative sign will signify that there is a 180 degrees phase difference between your input and your output there. Okay, so to solve for the bandwidth, so what do we mean by the bandwidth? So we just have to solve for okay, so we just have to solve for your F2, okay? Because our F1 is always equal to 0. So since this is equal to 0, automatically the value of your F2 will always be your bandwidth. So your bandwidth is your F2 closed loop. Okay? So we have to specify their closed loop because we already have a feedback. And that is equivalent to F unity divided by your closed loop voltage gain. So since we have a 741, our F unity is constant. So it is a standard value which is equivalent to 1 megahertz divided by our closed loop voltage gain which is equivalent to 50. No need to place the negative sign anymore because we don't have such a way that such as a negative bandwidth. So the negative sign is very important in the gain because the negative sign will signify whether you are inverting or you are using an inverting or a non-inverting amplifier. Okay, so we have here 1 megahertz divided by 50, so that will give you 20 kilohertz. So that means if we're going to get the value of negative 50 in terms of decibel, that will give us 34 dB. Okay, so from 0 up to 20 kilohertz, that is equivalent to 34 dB. So this is our F2. And from your F2, that will be your negative 3 dB point. So that will start decreasing at a value of 20 dB per decade until it reaches our 1 megahertz range. Okay, so that is what we mean by the bandwidth. Now, we are asked to solve for the output voltage if our frequency is 1 kilohertz. So obviously, 1 kilohertz is below 20 kilohertz. Since it is below 20 kilohertz, what does that mean? That means from 0 to 20 kilohertz, your gain is constantly equivalent to negative 50. So if we have an input voltage which is equivalent to 10 volts, all we have to do is to multiply it by negative 50 so we can get the output voltage which is equivalent to negative 500 volts peak to peak. Okay, so from 0 up to 20 kilohertz, our gain is equivalent to negative 50. Okay, or it will be increasing your input by 50 times. However, once it reaches 20 kilohertz, it will be decreasing by 20 decibels per decade. And our next question is, what will be the output at 1 megahertz? So at 1 megahertz, our V out is equivalent to negative 10 millivolts. It's not zero. Okay, it's not zero because 1 megahertz is the unity frequency for for a 741 operational amplifier. So what does that mean? At this point, we just have a unity gain. So what do we mean by a unity gain? So your input is just equivalent to your output, but with a 180 degrees phase reversal. Why? Because we placed your input at the inverting terminal. So that is how we solve a problem using an inverting amplifier. Okay? So this is very simple, class. Our computations are very, very simple. So it just has something to do with how you compute your voltage gain, and you just have to put in your mind that uh, until when your operational amplifier is working, and until what frequency will it not start to work anymore. Okay? So we have here another example. So actually this is an example of how your error voltage will affect your circuit. Okay, so what is the output voltage when your Vin is equal to 0? You use typical values. So what do you mean by typical values? If you're not very familiar with operational amplifier or your 741, it's just like saying that we have here an incomplete circuit or a circuit with an incomplete given. Or we can just say that maybe the output is also equal to 0. Okay, so what does that mean? And what are the typical values? Okay, so what are the typical values? So from our given circuit here, So for 741, our input bias current from our table, from our first video regarding operational amplifier, your input current input bias is equivalent to 80 nanoamperes. Your input offset current is equivalent to 20 nanoamperes, and your input offset voltage is 2 millivolts. Okay, so first we need to solve for your RB2. Okay, so first our RB2 is equivalent to R1 parallel our RF. Okay, so that is 1.5 kilo ohms parallel 75 kilo ohms, and that is equivalent to 1.47 kilo ohms. Okay, so all we have to do is to compute this using our given formulas. But since in our original circuit we don't have RB1, because our RB1, or the non-inverting input is grounded, so therefore we don't have an RB1 there. Okay, so what we have is your RB2, because it is the resistance in the base of our inverting amplifier. So if we're going to imagine a differential amplifier, so therefore, for our formula here, RB1, this is equal to 0, and this is 1.47. So this is equivalent to negative 1.47. Anyway, these are just direct substitution. Okay? Uh, the same is true with your V2 error and your V3 error. So V3 error is just equivalent to your input offset voltage. Okay? So you can see what is the effect of your closed loop voltage gain. So the closed loop voltage gain will minimize your your input error voltage. So why? How will it minimize your input voltage error? Because instead of multiplying this by 100,000 for an open loop voltage gain, we will just make use of the closed loop voltage gain, which is roughly equivalent to 50, which is 75 divided by 1.5. Okay, having giving us an error equivalent to plus or minus 107 millivolts. Okay, so what do we mean by compensating resistance? So the compensating resistance class is that from our original circuit, we can place, instead of placing, okay, instead of placing a this non-inverting input to the ground, we place here an RC. And this RC is equivalent to your RB2. So usually this is equivalent to RB2, or the nearest possible resistor available nearer to your value of RB2. Okay, so that we can nullify. Okay, so we can what do you call this? We can since they are, for example, RB1, so if we place an RB1 which is equivalent to RB2, so if we subtract this, this will be equivalent to 0. So therefore, we can at least nullify, or we can invalidate one error. Okay? And also, one way of decreasing your offset voltages and currents is by placing your nulling resistance. So if you can still remember, so you have a nulling circuit in pin number 1 and in pin number 5. So we place here a potentiometer, wherein we can adjust the value of the potentiometer so that we can decrease likewise the value of your offset voltages and your current. So those are just the different ways on how you're going to improve those error voltages. Of course, those are error voltages, and since it is error, we don't like that. Why? Because you don't have any input so supposedly you don't have any output. Okay, but since it is uh, non-ideal, once your operational amplifier was manufactured, there are already, okay, offset voltages and currents. So all we have to do is to at least minimize them by using these different techniques. Okay? Okay. So next is another basic op-amp circuit. Okay, so another basic op-amp circuit class is the non-inverting amplifier. Okay, so again, Just like the inverting amplifier, this also uses a negative feedback to stabilize the overall voltage gain. Okay, so this is the equivalent circuit for a non-inverting amplifier. As you can see, we still have a negative feedback because the feedback is still placed on the inverting input. However, we place your input at your non-inverting terminal. Okay, so part of the output voltage is fed back to the input through this voltage divider here. But our input is placed at the non-inverting terminal, therefore making this a non-inverting amplifier. If we have here your Vin, we have an amplified version here of your input signal, which is in phase with your input voltage. So we have here the input voltage Vin drives the non-inverting input. Okay, so the input voltage is amplified to produce the in-phase output voltage. So the voltage across R1 is the feedback voltage applied to the inverting input. Okay, so the difference between V1 here and V2 here must be very, very small. Okay, so why? Because if you can still remember, we also have such a thing as virtual short in our non-inverting amplifier. Okay, and this is how we are going to explain the virtual short in a non-inverting amplifier. So since Rin is infinite, okay, both input currents, both current at the positive and both current at the negative must be equal to 0. And also, since your AVOL is infinite, V1, the difference between V1 and V2 here is also equal to 0. So what happens here? The value, okay, or the voltage being brought back against V2 here will be equivalent to our V in here. So if V in is increasing, okay, we have a feedback here which is equivalent to your V in but in opposite polarity. So therefore, if we subtract them, the answer is always equal to 0. So if this decreases, the feedback here will also decrease to the same amount of our input here. So that is what we call bootstrapping. Okay? So the non-inverting input pulls the inverting input up or down to an equal value so that when we subtract them with V1 minus V2, the answer is always equivalent to 0. So that is our virtual short here. Okay, so how do we solve for the voltage gain? So the voltage gain here is almost the same with the inverting amplifier except that we add 1 to the ratio of the resistance. Okay, and also the output is in phase with the input, therefore there is no negative sign used. Okay, so how did we arrive with that value? Okay, so as you can see, whatever your voltage across your R1 here, that is equivalent or that is equal to V in because V1 minus V2 is always equal to 0. Okay? So, and since because of the virtual ground, okay, we know that no current must enter your inverting input. So your current I1 here is just equivalent to our current I1 here. Okay, so they are just equal because of the virtual short or the virtual ground. Okay, so if we're going to elaborate this one, what do we have? Okay, so our input there, by looking at the figure, that is equivalent to your voltage across R1. And the voltage across R1 is equivalent to your I input multiplied by your R1 here. Okay, how about your output? So our output is placed between, of course, the output terminal. So that is the whole voltage from RF to the ground, which is equivalent to your R1. And since the same current flows across RF and your R1, that that just shows that RF and R1 are in series because I in there is just equal. So what is your output voltage? So your output voltage is just the current multiplied by your RF plus your R in based on the circuit. Okay, and it's positive, right? Because the positive terminal is connected at the output, unlike in the inverting amplifier. So your V out there is equivalent to I in multiplied by the sum of your R1 and your RF. So getting now the voltage gain. So we place here a closed loop voltage gain because we have already a feedback. So that will give you V out all over V in. Okay, so our V out is equivalent to I in R1 plus RF divide by, you have here I in multiplied by R1. Since we have the same R in, this will just be canceled out, and that will give us R1 plus RF all over R1. Okay, simplifying this will give us 1 plus RF all over R1, which is the voltage gain for a non-inverting amplifier. Okay, so if we wanted, for example, a gain equivalent to 50, so we're going to get a combination of RF all over R1 that will give us 49. Okay, because we still need to add 1 so that we can have a gain which is equivalent to 250. Okay, so the only difference between the inverting and the non-inverting is, of course, we don't have a phase reversal, and at the same time we have a plus 1. And of course, you will be placing the input voltage at the non-inverting terminal. Okay, so the circuit is very simple. All you have to do is to place R1 and your RF. Okay, so that is the non-inverting amplifier. So what is the counterpart of the non-inverting amplifier in our previous topics? Okay, so the non-inverting amplifier is like the common base configuration, because the common base configuration is capable of producing high voltage gain and it has no phase reversal. So the counterpart of the inverting amplifier is the common emitter configuration, and the counterpart of the common base is the non-inverting amplifier. Okay? So for the other quantities, it is the same. So it is the same with what we have discussed in the inverting amplifier. So the voltage gain can be a trade-off with bandwidth. Okay, so do you want a higher voltage gain? Then we have a lesser bandwidth, or if are we going to accept lower voltage gain and have a wider bandwidth instead? Okay, so the negative feedback increases the input impedance. So the input error voltages caused by the input bias current, input offset current, and input offset voltages are analyzed the same way as with the inverting amplifier. And at the same time, your RB2 is also equal to R1 parallel RF. Okay, so what is the effect of the output error voltage? So your output error voltage reduces your peak-to-peak, maximum peak-to-peak voltage. Okay, so the greater the output error voltage, the smaller your peak-to-peak value. So for example, if we have here a plus or minus 15 volts. So we are expecting roughly 30 volts peak to peak. But in reality, we can only have at least 1 to 2 volts difference. So that is given by plus and minus 14 or 28 volts peak to peak. But if we have an error voltage, we can just have a 20 volts peak to peak output voltage. So what causes the lowering down of your output voltage? So this is due to the error voltages. So if we can, okay, we wanted to eliminate those actually, if we cannot eliminate it totally, at least we lower down so that we can still have what we wanted output voltage that we designed for. Okay, so that's it for our second video regarding our operational amplifier. So I just discuss the inverting and the non-inverting, because when we know the inverting and the non-inverting, it is already very simple or easier to understand the other applications for an operational amplifier. Okay, so for our third video, we will be discussing more applications for our operational amplifier. Okay, so again, thank you for watching, and don't forget to hit the like button after watching. Okay, so thank you very much and God bless.